Sorry for the slight delay. We are waiting for some participants to come in. Today, this morning or afternoon or evening, whatever it is for you, we will talk about co-treatment of fecal sludge or septage in sewage treatment facilities, right? So this is a topic of much interest in many parts of the world now, where people are looking at utilizing existing sewage treatment plants for this kind of purposes. Some of the things that I will be speaking about, many of you may be already familiar, and it might appear to be quite basic, but to cater for the wider audience, we will cover some basic aspects as well. So please bear with us on that. So today's agenda, we will first have a short presentation by myself introducing co-treatment, the principles, and evaluating the various factors that are relevant to co-treatment. Then we have a worksheet tool that has been developed. It's an Excel sheet tool, which will then be introduced, and there will be a demo of the use of that the tool, and finally a review and discussion. So this is basically the agenda that we have for this afternoon. So first, the introduction. So this is basically a sewage treatment plant. We have adopted a common type, which is an activated sludge system. As you know, most of you would know that it consists of physical processes and physical biological processes. So the upfront, the part of the treatment facility are usually the physical processes, pumping, screening, grit removal, and primary settling, right? And then you have the aeration tank and the secondary clarifier, which together functions as a physical biological process with microorganisms doing the work. So this is what a sewage treatment plant is about generally. And now we are going to add septage or fecal sludge into the inlet of this sewage treatment plant. And then we are now concerned, when we do this, what are the impacts that might happen to the processes that is going on, right? So this is basically the topic we are talking about. So when we talk about fecal sludge or sewage or septage, this fecal sludge or septage is different from sewage. And even though the origin is pretty much from human excreta, sewage originates from human excreta and wash water, and also some gray water that comes from bathrooms and kitchens and things like that. But septage also comes basically from human excreta, and sometimes the gray water is added as well, but it's not. In most cases, it's not. But then it is channeled through a containment, which could be a septic tank or a pit or some kind of a containment. And then if we look at a typical septic tank, for example, this is a diagram that shows a typical septic tank. The inlet, you can see the sewage actually gets in on the left-hand side through that T-pipe. Then there is some settling that is taking place where the solids settle to the bottom. There is some consolidation that takes place. Sometimes if there is a leakage of groundwater into this, then there could be a dilution. And there will be some anaerobic digestion of the settled solid. So this is these are the processes that are going on inside. And when we look at this containment, this is a proper septic tank, which could be watertight, but it could have also, you could have a septic tank which does not have a proper bottom. So you can have gray water, groundwater seeping in, and or you could have the water from the containment itself seeping out continuously. So depending on the type of containment, the sludge settlement, the processes vary, and that is what makes the fecal sludge different. And when we talk about fecal sludge or septage, it's actually emptied from the bottom of the septic tank or containment together with whatever liquid that is present above it. So that would constitute septage. And if it is a pit, for example, you might have very little liquid on top, so it becomes much more solid and much less liquid component to that. So that's basically what it is. But you can see from here also that the bulk of the water that enters, the sewage that enters, after settlement, the clarified water exits the containment. So it's actually leaving the containment either through the outlet onto a soak pit or to a filter or to the drain or wherever, right? So only the solids are being retained. So the bulk of the fecal sludge or septage consists of settled solids, which have also undergone some kind of anaerobic digestion. And this makes fecal sludge or septage very different from sewage. In terms of volume, much of the volume has already exited through the septic tanks. And the solids content can be different because obviously the solids are being retained. So the fecal sludge or septage contains much higher solids content as compared to sewage. The BOD or COD will be different, will be much higher for fecal sludge or septage. The inorganic content and garbage content could be high because many people abuse these things, and sometimes it does not have a proper base. And therefore, when the desludging is done, the bottom mud and sand and things like that also comes through. The biodegradability of fecal sludge or septage is also different. We will see this subsequently. Then the variability. Sewage is, it is variable, but not that much. Whereas the septage can vary from tanker to tanker, from place to place, because the way it is coming from different containments and there's not much of mixing that is taking place. And finally, there's a potential contamination of fecal sludge or septage by toxic or industrial waste. The reason is because these tanker which are emptying the containments, they could also be taking some industrial waste from somewhere, which, you know, if the control is not very good, then that ends up in our treatment facility as well, right? So this is what the key differences are. So now going back to the sewage treatment plant, which is having this septage coming in, we need to understand by these differences, how will this sewage treatment plant, which is designed to treat sewage, now it's also going to handle fecal sludge, which is very different. So how will this impact the different processes in the sewage treatment plant? And what can we do about it to mitigate? What can we do about it to minimize? Can we do something to the sewage treatment plant so that the risks to the plant are minimized and the performance is not impacted greatly, right? So this is our task today. So what can go wrong? So number one, the flow could be too high, right? So if the flow is too much compared to the design, then the settleability in the settling tanks, the primary, the secondary, and so on, that could be impacted. Retention time becomes shorter, which means process time becomes shorter. And there could be washout of whatever solids or things which are retained within the tank. During high flows, it could get washed out. If we can have too much solids. So since we know the fecal sludge and the septage has very high solids content, this could now overload your screening step or your grit removal or your primary solids removal system in your primary settling tank. Secondly, your oxygen transfer efficiency could be impacted because in your aeration tank, you have a lot of inert solids floating around. There could be solids carry over to your secondary clarifier and overloading of the secondary clarifier. And if you're using a pond system, for example, the ponds could get filled up much faster by the additional solids that are coming in. And it may require desludging at a more frequent intervals, right? Too much of organics, BOD or nitrogen, because of the co-treatment, then will result in insufficient reaction time for the microorganisms to do their work, or insufficient oxygen to actually treat the total nitrogen and BOD that is now coming into the system. Shock loads, because of uneven application of the loads, the microorganisms will be unable to balance between the incoming waste and the total population of microorganisms. The variability of the characteristics, again, the microorganisms need to acclimatize. If you have a sudden influx of very high strength waste coming in, the microbial populations will be unable to adjust and acclimatize on time and be able to do the work of the treatment efficiently. And finally, you may have some toxins which may then kill off the microorganisms or inactivate them. Right? And finally, there's also potential where the septage or fecal sludge is added not to the treatment plant itself, but to the sewer manholes or to pump stations. Usually people do this as a matter of convenience, and this may cause blockages, grit and garbage settling in your sewers, pumps clogging, and erosion and blockage in your pumps and the pumping system. So this is another impact that could be going wrong. So these are some of the things to watch out for. Now let's look at the first part of it, which is talking about the volumes, relative volumes of sewage and fecal sludge or septage and the variations. So here we take an example of a city which has a population of about 200,000 people. And let's assume for convenience that 50% of those are having a sewer sanitation. So they're connected to sewers. And the other 50% is having a non-sewer sanitation using septic tanks or whatever. And then, so this pie chart here shows 50-50 split of the type of system. And now, when we look at the total sewage that is generated from this 50% which is sewer, and the total fecal sludge or septage that is generated from the other 50%, this is what we get. The septage volume is so small, and the sewage volume could be about 100 times or more compared to the septage volume. The reason we could have seen earlier is that the bulk of the liquid that enters the septic tank after settlement leaves the septic tank and leaving only the settled solids behind, right? But in the sewer systems, the entire contents are conveyed through the pipelines and reaches the treatment plant. So in terms of volume, this is what happens. And this, we are talking about a daily flow. So a daily flow has maybe 100 times more in terms of sewage compared to septage. But let's look at the variation over the day. This is a typical sewage flow variation. The graph here shows over a day, 12 midnight to 12 midnight. And you have a typical 2 peaks, a morning peak and an evening peak, corresponding to the water usage by people, right? So when more people use water in the morning, so you get a high peak in the morning and then an evening peak again. The rest of the time is lower. So this is how the sewage normally varies as it reaches the sewage treatment plant. But how does the sludge flow vary? So here, the sludge flow does not vary in the same way. It depends on the operating hours at which the sludge is received in the treatment facility. Usually, it is normal working hours of 9 to 5, for example. So that's when the tankers arrive. And then it depends on the tanker volume, how many tankers arrive, the frequency of the emptying of the containments. And there could also be a seasonal impact. And on weekends, if the tankers are not working or the reception facility is not working, you get no flow. So the pattern of flow of septage or fecal sludge is very different from sewage. So when we mix up these two in a co-treatment scenario, you can expect a little bit of a variation, right? Now here we are. This is the same graph of the sewage variation over the day, similar 2 peak. And now let's superimpose the fecal sludge onto this. And this is what happens. You can hardly see the impact. So because here at the bottom, this is where the sludge is being added from 9 to 5, very small quantities as you saw. The equivalent quantities are very small, right, for the same population. And here, during this peak period, and also during the time which corresponds to when the tankers are discharging, it's a very negligible increase in the flow, right, the flow pattern. So what we can conclude is that the flow itself for co-treatment may not be a big issue of concern, right? Unless you're adding huge quantities, which in any case, there will be other limiting factors. So flow itself is not the main criteria that we should look for. Now let's look at this concept of flow, concentration, and loading. We saw the flow, that the flow is inconsequential, but we know that the concentration of total solids, for example, in fecal sludge or septage is very much higher than sewage. It could be 10 times more, or it could be even much more than that. But what is of concern to us when we talk about the treatment efficiencies of the treatment facility is the total loading that comes in. And how do we get that? It's a flow multiplied by the concentration is what gives us the loading. So even though the flow variation is small, because the concentration variation between sewage and fecal sludge or septage is very different, very much higher, then the loading could be significant. All right. Now let's look at this again. The flow, this is what it looks like, quite insignificant. Let's take a total suspended solids concentration of sewage about 300, which is typical. And let's take 7,000 for our sample of septage, which is actually on the low side, if you ask me. So you can see that it's very much higher, more than 10 times higher than the concentration. And when we multiply and get the solids, you see it is significant now. It is more than 10%. Earlier, you saw that the flow increase was not even 1%. But when it comes to the solid loading, it is already much higher. And similar ratios will be seen for the BOD loading or the nitrogen loading as well, right? So similarly, you'll find that the loading part of it can become significant. And here we have done this on the first bar on the left-hand side is the flow. The blue part is the sewage flow, and the red small tiny thing on top, that is the flow due to septage. You can see it's insignificant. But when it comes to solids, it becomes a little more significant, BOD, a little significant, and also nitrogen, right? And this, again, we are talking about the total over a day, right? But what happens when we look at the variation? Here's the variation of suspended solids coming to a sewage treatment plant due to the sewage. So the pattern follows the pattern for a sewage variation as well. So when the sewage peaks, the total solids peaks, because you know volume multiplied by concentration is the loads, right? So this is what it is. Now let's superimpose the solids due to fecal sludge or septage being added during the working hours of 9 to 5. This is what happens. Even though a small quantity, you might find that the daily impact is not great, but the hourly peak impact here, this can be quite significant, right? So what does this mean? This means that if you have a process, a treatment process, where your process time is short, and if that short process time falls within this peak period, then it could have significant impact. But if you have a treatment process which has a long process time, for example, an extended aeration, it can go up to 18 hours or even more than that. So then the loads tend to even out over the day. But in this case, when you have like an SBR, for example, which has a very short period for aeration time, the cycle times can be short. Then this kind of impacts has to be checked, and hourly peak may need to be checked, right? And similar patterns can be seen for BOD loading as well as nitrogen if we go for that, right? So this is a problem for short duration, and maybe with the equalization tank, an equalization step or a balancing tank, this could be mitigated. Now let's look at the organics itself. So far we talk about BOD as if it's just one number, right? So when we look at the organics fractionalization of that, let's start looking at the components of that. What is it made up of? The different types of biodegradability, for example. No? So here we have a digested fecal sludge or septage. What does that mean? Mostly our fecal sludge or septage comes from a containment where it has remained there for maybe a year or maybe a few years, often, because your desludging frequency could be in the range of 2 years, 3 years, or even more, right? So during that period, most of the organic matter has already undergone stabilization, and it has become inert matter mostly, and is no longer readily biodegradable. So this digested fecal sludge or septage, which is the common kind of fecal sludge or septage, which comes from pits and from septic tanks, which are emptied on a frequency of maybe a year or more. Very high percentage, maybe in this case I'm showing is a typical of more than 50% is already non-biodegradable, right? But it is particulate, which means it can settle out. So this non-biodegradable waste, if you pass it through a biological type of treatment facility, it does not really do much for us, right? So what it really means that we need to now look at this particulate aspect of it, and maybe we can remove it by some other means, a physical means, right? By settling it out. So this is the digested fecal sludge. Now we also have, now we also have fresh fecal sludge. Fresh fecal sludge has not remained in the containment for a long period. These are containments which usually, in public toilets or in community toilets, for example, which get emptied on a very frequent basis. They could be emptied on a weekly basis sometimes, maybe a month or so. And because of the frequency of emptying, the fecal sludge inside, the settled sludge inside, does not have much time to undergo degradation, right? So you find that the readily biodegradable portion is still very high, and there is still a big chunk which is slowly biodegradable, which means it has undergone some level of stabilization, but not so much, right? So you can see that the component of the biodegradable component is much higher for fecal sludge compared to digested sludge. This tells us something about how should we approach the different types of sludge depending on whether it is fresh or digested. And this is the whole picture which you can see here, that you find that the readily biodegradable part for fresh fecal sludge or septage is very high, 90%. And the particulate part is small. And secondly, the fresh fecal sludge also does not have very good settling properties, which means it doesn't settle that easily. Whereas digested fecal sludge settles much better, and you might be able to remove 55 or even more than that by settlement alone. And you only need to handle the remaining part in the co-treatment process. Here's a schematic of a co-treatment where we are doing a direct addition of the fecal sludge to the septic tank. And this is something that has been done historically. If you look at it, people do this. So they have an STP and they just dump the fecal sludge to the inlet without any kind of a pre-treatment or any kind of a pre-settling or screening or whatever. So it just goes in. And this is not a very good practice unless the quantities that you are adding are very small or the strengths are very, very low. So I would say that we don't do this unless you have a very tiny portion of sludge compared to the capacity of your treatment facility. Otherwise, you might have an upset in your treatment facility. The second one here is for fresh septage or fecal sludge. So you find here, this is highly biodegradable, and you may need a stabilization step here. This could be a digester or the stabilization tank, where the incoming sludge is settled and digested, and only after that the liquid then is co-treated here, right? And the solids could be co-treated in the solids part of the treatment facility. And here is typical characteristics of fresh sludge, COD, BOD ratios, and things like that, and some methods by which you can do it, the stabilization. And the effect of the stabilization is that your BOD gets reduced, the solids get reduced, and the solid liquid separation becomes much better, okay? And this is the most common, where the solid liquid separation followed by co-treatment. So as I mentioned, most sludge comes from septic tanks or pits where it has remained for a pretty long time. And therefore, a very big chunk of it is particulate and non-biodegradable. So we have a screening and grit, and then you have a solid liquid separation step here. And only the liquid part is then co-treated in the STP, whereas the solids can be either co-treated in the solid stream here, where combined together with the sludge coming from here, or it could be a separate stream for the solids coming from here. So this is the most common one. And you can have different types of solid liquid separation processes to be used, drying beds, anaerobic ponds, belt press, and so on. And you can see here that the percentage of total solids reduction can be a very high percentage, which means if you're using drying beds, for example, only 5% of the solids are then in the filtrate that is coming out of the drying beds. And similarly, there's a reduction of big portion of the BOD as well, right? So this is a good step to do so that you actually reduce the kind of loadings that end up being co-treated in your STP, right? And this one is if you have very dry sludge, where it's not even necessary to do a solid liquid separation before this. So you could have like a drying bed, for example, and apply the dried sludge directly onto the drying beds. If the sludge is already well stabilized, and if it's a very high solids content, and only the liquid part that comes out of the underflow of the drying beds will then need to be co-treated in the STP. So this is another step which could, again, all depending on the type of sludge that you're handling. It is possible that a city has both fresh and stabilized sludge coming to their facility. Then we need to make a decision. Is it good to blend it, or is it good to have a separate streams for the two types of sludge? Whatever, depending on the relative quantities that will be required to handle in that particular city. Okay. Now let's look at the impacts that we can expect when we co-treat on a treatment facility. What kind of risks can we expect, and how can we mitigate those risks? So the first thing we can expect is that there will be an increase in the sludge and scum because we are adding very high solids to it, and that will cause increased primary sludge, for example, even secondary sludge. And significantly higher organic and solids loading will be experienced by the STP. There could be shock loadings because of irregular addition of sludge, unless we have some kind of blending or some kind of stabilization, some kind of equalization tank. And potential toxic substances may be there. We need to take precautions for this. And screenings and grit volumes will also be high. You can expect this, right? So these are the general things you can expect as impacts on your STPs when you do co-treatment. Now, on the liquid stream itself, let us assume that you have done a solid liquid separation, and then you are now adding the liquid part after solid liquid separation to your sewage treatment plant. First impact that is possible is that there is insufficient aeration capacity for the combined sewage sludge load. As you know, the STP has been designed only for the sewage load. Now you added additional organic loading, and is the aeration capacity sufficient? Something to be checked, right? And secondly, there could be a lower oxygen transfer rate because of the higher solids in the reactor, both dissolved and suspended, and that could cause the treatment facility to have less efficiency, in terms of oxygen transfer. Mixing effect, usually the mixing in the aeration tank could be by mixers or through the aerators itself, creating a mixing. And because of the high solids which are in suspension, that the mixing effect could be less, right? So this is another thing that is possible. Higher solids loading and residence time in your reactor, higher surface overflow rates of clarifier, considering possible lower settlability, because the settlability is low, that could cause overflow of solids out of the clarifier, both primary and secondary. Higher oxygen uptake for nitrification. Ammonia content in your sludge will also be high, and that will take up some oxygen where nitrification also takes place. And if you are using, if you are doing a denitrification with an anoxic zone, then you need to have an organic carbon source, and there's a possibility that this is insufficient, right? So these are some of the things we have to watch out for. And later, when we look at the modeling, you'll find that we are looking at many of these things to see where the risks and how can we mitigate them. And obviously, the note down there says, if you have a solid liquid separation, then many of these things are minimized, because you're removing much of the organics, much of the solids ahead of the co-treatment part itself. When we have nitrogen removal, if your STP is increasingly, many countries are having standards for nitrogen removal, nitrogen or phosphorus removal. And nitrogen removal is done through two processes of nitrification and denitrification. And nitrification requires oxygen, so there will be a take-up of oxygen for that purpose. And if your STP, if your sewage treatment plant is designed to remove nitrogen from the sewage, you also need to check whether the additional oxygen that is required to remove the nitrogen from the sludge, the sludge, is that sufficient? And for the denitrification, again, the carbon source, as I mentioned. So the readily biodegradable carbon must be available for it. And usually in a sewage treatment plant, when we do denitrification, it's recycled. The flow is recycled to the head of the plant, and the incoming sewage is the source of of carbon. Here we have to check whether the combined wastewater and sludge has sufficient carbon. And the way it's done is to see that the BOD to the total gel nitrogen ratio should be at least 3. So that's the recommended ratio, to ensure that there is sufficient carbon source for this. Now let's look at different processes other than activated sludge. In a sequential batch reactor, this also works on a similar principle of activated sludge, but it operates on a batch mode. So you have different batch modes of fill, aerate, settle, and decant, that kind of batch modes. And each of these sequential, the mode, could have a very short time duration, right? And because of this short retention time, your instantaneous flow or the hourly peak flow may need to be checked, unless there is an equalization tank that has already been provided. And in any case, we need to check what is the peak flow after equalization, right? And process control should be managed to adjust the sludge wasting rate, the reaction times, and so on, to maintain stable conditions. In a normal activated sludge plant, is a complete mixed reactor where the entire contents are completely kept mixed. So you don't need to worry too much about it, because it sort of gets average out over the day. Whereas here, over the cycle, it settles, and then the sludge is remaining, becomes the return sludge for the subsequent cycle. And again, the biomass that is coming in could be different from the biomass that was already there in the earlier cycle, because different tanker loads could have different characteristics, and that could cause some acclimatization issues as well, right? In ponds, these are generally quite resilient, because ponds have very long retention time. So variations in flow, it's quite easy for them, for these ponds to handle. And if you have an anaerobic pond followed by a facultative pond, then you could, a lot of times, when you have very low solids content in the sludge, you could add directly into the anaerobic pond without a solid liquid separation, right? Provided it's a dilute sludge. But what will happen is that when you don't do a solid liquid separation up front, a lot of the sludge comes into the pond and it settles out there. And your anaerobic pond will start filling up with solids and sludge very quickly. And this may require desludging of the ponds on a more frequent intervals. Normally, ponds may take about 10 years or 15 years before you need to desludge it, and that's a very expensive and disruptive process. And if you co-treat very high quantities of high solids sludge, then you might find that you may need to desludge the ponds on a much more frequent duration. And the potential impacts, we need to also check that there is sufficient solid, there's the solids loading rate, volumetric solids loading rate for the anaerobic pond, and the surface loading rate for your facultative ponds. These are criteria not to be exceeded. And for the volume reduction caused by sludge accumulation, that could also impact the treatment in the pond itself, right? Next, we'll look at one more system, the upflow anaerobic sludge blanket reactor. This is an anaerobic system. And here, organic loading rates are important. And upflow velocity need to be checked under the co-treatment conditions. And sludge retention time, because maintaining the sludge blanket is very key to the proper functioning of these kind of systems, right? So this again is so sludge production retention time and the volumetric loading rate. We need to check that under the co-treatment conditions. Now let's look at in terms of planning perspective, right? In a city planning perspective, how do you look for co-treatment opportunities and co-treatment options, right? So this is how mostly the city managers are faced with this kind of dilemmas. So if you have a city, for example, then the first question to ask is, does the city have a sewage treatment system now, or is it planning to have one in the near future? This is the first question. And of course, if you say no, then the potential of a co-treatment is just non-existent, right? So you could then have two options of either looking for any neighboring cities where we could sort of have a cluster, right? This is being done in some places. So you could cluster with a neighboring city. So if the neighboring city has an STP, then possibly the sludge from this particular city could be taken to that city for co-treatment, or even if it's a fecal sludge treatment plant. Of course, it depends on the distance, right? It should be reasonable distance. And if no, there is no potential of that, then of course, your only option is to have a fecal sludge treatment facility, a standalone one, right? So there's no co-treatment possibility here. So we construct a fecal sludge plant. Now the answer is yes. A new sewage treatment plant is being planned for the city. Now this is a good option, a good scenario in the sense that we have not built anything yet, so it's being planned, and therefore we can evaluate the logistics of using the new sewage treatment plant for the purpose of co-treatment. Look at site availability. Is there enough land within that site to accommodate whatever pre-treatment or whatever other ancillary facilities that you are planning as part of the co-treatment scheme? Suitability of the site, maybe whether there is any residential or sensitive areas nearby which may have a problem when your tankers start moving in and out and so on. And then we can incorporate co-treatment as part of the design. So this is very easy because you have not built anything, and you could just say, okay, this is what we are expecting over that planning period, and this is my STP, and we can plan it and design the STP to co-treat, right? Quite fairly straightforward. Now, when you have an existing STP, it gets a little more complicated. Again, you still need to do the logistics evaluation. Is the STP close enough so that the tankers can move to that place easily, and there's available spare capacity? If the STP is already almost fully loaded, or you expect it to be fully loaded in the next 1 or 2 years, or if the performance of the sewage treatment plant is not up to the mark, it's risky, right? Then you may have second thoughts about doing co-treatment here. And what other technical constraints are there for co-treatment? This is the evaluation you may need to do. And then you decide what kind of pre-treatment is needed, what modification may need to be done to the sewage treatment plant, any retrofits that may be needed to accommodate the co-treatment. So this will be your way of trying to see whether you can co-treat at the existing STP. And the opportunities are mostly where there are sewage treatment plants which are underutilized and expected to be underutilized for the near future, within your planning time frame. And existing STPs can then be used with or without retrofits. And new STPs, as I said, can be designed, and then there's this opportunity for clustering with the neighboring towns which are within reasonable radius of 10 to 12 kilometers. Now, we can also have, these are not mutually exclusive. In other words, we could have part of the city having a co-treatment and part of it going to a standalone STP, standalone fecal sludge plant, depending on the logistics. If your city is very big and the sewage treatment plant is at one end of the city, it may not make sense to transport fecal sludge or septage from the other end all the way to the sewage treatment plant. So it may make sense. So here is where your economic analysis will come in. Is it better to co-treat in that place, or is it better to have another fecal sludge plant elsewhere, and many other options? So you could have combinations of options for the city. So the options are these: dedicated FSTP or co-treatment, or combination, or multiple, interim or permanent. So you could have an interim arrangement. We'll do this for the next 2 years. After that, we will build a fecal sludge plant, for example. The logistics, some of the logistics could be overcome through the remote addition of sludge at pumping stations, for example, but it should be done properly. Whether you want to do a solid liquid separation, whether you need to do a digestion to stabilize fresh sludges and so on. And the influencing factors are these: availability of the plant, the size, capacity, and so on, logistics, site availability, what are the relative volumes of fecal sludge as against sewage, the nature of the sludge, whether you are going to be reusing the end products of your sewage treatment plant. Why? Because if there is some toxic substance in the sludge that is being brought in by the tankers, and that ends up in the sludge, in the STP, and as a result of that, your end product, your biosolids produced in the STP becomes contaminated and unfit to be used for certain purposes. For example, you may be using it for as an agricultural, soil replenishment or some kind of thing like that. The biosolids then become unsuitable for that purpose. And the final point here on the institutional is again a very important point. Now, who is running your sewage treatment plant? That could be one entity. It could be the city. Who is doing the fecal sludge? That could be another entity. So we have come across in many countries, these are two different entities. And therefore, the person running the sewage treatment plant is reluctant to allow fecal sludge or septage to be co-treated in the STP because they don't want to take that risk. It is not their jurisdiction. But if the same institution is doing both, then it becomes much easier. So you'll find that institutional conflicts sometimes prevent co-treatment from being done. It's one factor to be considered. This I just want to talk a little about this discharge of the sludge at manholes or pump stations. So this is very convenient and it has a logistical advantage because manholes are everywhere. Pump stations also at many locations compared to the sewage plant maybe only at a very far location, and it may not make sense for the tanker operator to go all the way there. So when you allow this, you'll find many people take advantage of this. But there are many downsides to this, which we must consider. Number one, solids being deposited in sewers and causing blockages, pumps being increased wear and tear because of sand and grit that's coming in, abrasion of the pipes again due to grit, oil, grease. These tend to be very high in septage or pit sludge, right? And these cause clogging and blockages. And if it is a remote location, a manhole, for example, where people can just open the manhole and start discharging inside, then the control and monitoring of what is being discharged becomes extremely difficult, right? So this might end up with an abuse where people just dump whatever they like inside and no one is watching this, right? And there's a high risk of toxic or incompatible waste can be dumped inside. And by the time you detect it, it's too late. Maybe a sewage treatment plant or even your sewerage system has already been affected by it. Okay, these are some of the things. So we then must have a proper way to provide decanting stations so that the logistical advantage of remote addition can be taken advantage of. At the same time, we can have some safeguards like having a screening, a grit removal, and possibly a solid liquid separation process in these decanting stations before the liquid part is co-treated. And of course, we may have some kind of monitoring facilities where there's somebody there who's taking care to see what is being discharged and maybe checking where these tankers are bringing the sludge from. Let's look at operationalizing it now. Co-treatment, once you have decided you want to do it, the first thing I would recommend is start small. Don't go big time. Start small. There are many, many unknowns here, which we have tried our best to find, but you might find that something can crop up. So we can start small, keep the risk low. And as we learn, as we find that the risks are okay, is within our appetite, then we can slowly scale it up. Select only large sewage treatment plant. Don't go for small ones because the tendency for upsets is very high in small sewage treatment plants. The larger plants usually are more robust. They have more skilled people running it, and they have more safeguard systems. And also, because they are large, they're able to accept a higher volume of sludge in comparison with small ones. And there will be a justification to spend some money some funding to put in facilities for pre-treatment and some ancillary facilities as well, right? Whereas when you have a small one, it may not justify this, right? Secondly, it's not enough to be large, but it should have sufficient spare capacity, which means if the plant is designed for a particular capacity, the current flow that is coming in should not be very high, should not be 95%, for example. No? If it is 80% or even 70%, then that is a spare capacity which could then be utilized for the co-treatment. The end products I've already mentioned earlier. The logistical part I've also mentioned. We can look at logistics and try to come up with a remote decanting station that would certainly improve the attractiveness of co-treatment. The cluster basis, that's a very good approach that should be tried as well. The institutional issues, these are real and must be addressed right up front. The variability of sludge is an issue, and every tanker could be different. And there should be some kind of a check on the incoming septage. Besides, if you can have a system of regulation where the tanker operators need to have records of where are they bringing the sludge from, and there is some accountability placed on the tanker operators of the sludge that they are dumping in. Right? So for new facilities, it's easy. For existing facilities, this is what we have to look at. What is the pre-treatment we need to put in? Whether you need to have an equalization, you need to regulate the tanker operators and monitor quality, increase the solid handling capacity in your sewage treatment plant, increase oxygen supply, and so on. Here, I will sort of going to stop here, but this is to decide on the existing sewage facilities, how can we carry out co-treatment, and what kind of impacts can we expect, what kind of risk can we expect, and to give some indication of what we could do to mitigate those and still carry out co-treatment is what the purpose of the worksheet tool, the co-treatment worksheet tool, which will be demonstrated after this by my partners, the CDD team. Here, I just want to give these two links, which has been shared earlier. So there is a book on co-treatment. This book has been published by IWA, and it is available online also for free download. But in this link, you can find an updated version of the book. So I've done a little bit of updating, and it's brought to 2021. The earlier one was 2019, right? And then the worksheets are also downloadable. These are Excel sheets, which can be downloadable from the link that is also shown here. And with that, I've come to the end of the presentation. Thank you so much. And I will now hand over to the CDD Society team of Krishna, Ananda, and Debisha. And they will demonstrate the use of the worksheet tool. And also, then after that, we can have some discussions on what your thoughts are. And our whole idea is to expose this to as many practitioners as possible and get some feedbacks. And it's not perfect. And some of your feedback could be then used to make this better for common use by everyone, by all practitioners everywhere. It's a planning tool, it's not a design tool. I just like to remind on that. With that, I will call on Krishna, Ananda, and Debisha to take over from here. Thank you so much.
Thank you, sir. Yes, can you hear me? Yeah. So there is a question by Mr. Chris Chan on how do we deal with heavy metals, and what will be the effect of heavy metals in such kind of a situation when we co-treat? Will it be any different from, because heavy metals can be also in the sewage, but will it be adding a lot of load if we are putting FS into the sewage treatment plant? Will the heavy metal concentration shoot up like anything? Can you throw some light on that?
Yes. Normally, sewage treatment plants, they will not have heavy metals because it is usually taking domestic waste. Unless you have a combined system which also takes industrial waste, in which case your sewage treatment plant might have some treatment steps to deal with that, right? So if it is not compatible to a biological treatment system, then it will cause upsets. And why I mentioned this in this particular case is because when you have sewage treatment plants, the sewage is coming from connections from houses, right? And so it is a much more physically constrained system where some industrial waste usually is not so easy to be connected inside. Whereas when you have a tanker-based operation, the tanker could be dislodging from an industrial premise, and they might be taking waste from an industrial process. So there could be a process waste that comes in, right? So the risk of such things happening is much higher when you are considering uh, a co-treatment. That is what I mentioned. But if your sewage is already having some heavy metals and it is already being designed to cater for that, of course you need to check whether by co-treating it is going to add substantially to the load and how it impacts. What we have considered is basically the normal domestic sewage load. It has not looked at the industrial kind of load in this. I hope that answers.
Right. Thank you, sir. I think yes, there is one more question by Jonathan. It is, what is your experience on problem of high solid waste in FS?
Yes, so solid waste in FS, we don't have that much in Malaysia because our septage comes mostly from septic tanks and not that much from pits, right? But when you have these coming from pits, where sometimes people use these also as to dump garbage, right? I'm not saying ours, we don't have any, but we do. But normally the normal screening process will be able to handle that, right? So a lot of times your emptying itself becomes a problem if there's too much of garbage in the pits or in the septic tanks. It gets clogged even at that time, right? So it is not a problem of it upsets the entire process because normally a screening will remove solid waste like garbage and things like that. So I would say in terms of experience, we don't have that much, but I've seen pit latrine emptying especially, where the emptying process itself is hampered by solid waste inside the pits. So they need to use rakes or things like that to remove the solid waste, or use some specialized kind of equipment to empty the pits also. Right? Yeah. Thank you.
Yes. I can also see that Anand wanted to add to something on this answer. Anand, would you like to go ahead?
Yeah, please.
Yeah. So the solid waste with associated fecal sludge, let's come from mostly the users who are using the toilet as like outside, like public toilets, where you can see the disposal of napkins, disposal of bottles, disposal of all plastic covers are being disposed there. And usually we also see in Indian context where institutional septic tanks are being emptied, the quantity we at FSTP Devanali, when we looked at it, the quantity ranges from 2.5 kgs per load. The per load, I mean 4 cubic meters. So we have also seen maximum of 5 to 10 kgs of solid waste being received at an FSTP. So this usually differs with respect to the user behavior, and which we can address by IEC campaigns and educating them not to do it. And any treatment plant, let it be an STP or FSTP, a proper screen chamber has to be there to prevent any blocking or clogging of the process in the modules downstream. So that is very essential for that.
Thank you, Anand. There are 3 more questions. We'll quickly take them and then we'll move to the next section of the presentation. So one, Mr. Kapanda asked, Kapanda asked that what is the best way to deal with the situation where you have varying degree of biodegradability in the sludge, fresh versus stabilized sludge in the context of co-treatment. So he's asking how will fresh sludge versus stabilized sludge affect the co-treatment process?
Yeah. So when we have fresh sludge, it is highly biodegradable. And so if the quantities are small, you could directly add into the STP, because it is just like sewage mostly. It's slightly stronger than sewage. But if the quantities are large, you may need to have a stabilization tank to sort of remove, bring the BOD of the fecal sludge down to a more reasonable figure, and then co-treat. So that's what I would do with the fresh sludge. Whereas if you have well stabilized sludge, it is very easy to do a solid liquid separation because settleability is much better. So we can do a solid liquid separation to remove a lot of the solids together with a big chunk of the organics as well, and then do the co-treatment. So I believe Mr. Kapanda is from Lusaka. I can't recall, but I remember that the sludge from Lusaka was from pits, but was said to be very high, biodegradability. So I think that kind of sludges may need a digester before co-treating in STP. That's what I'm thinking. That is possible there. Yeah.
Okay. Thank you, sir. Anand, yes. Would you like to take the next two questions? One is on co-treatment in anaerobic systems, and the other one is the implication on the ONM. Yeah.
Thank you, Divisha. See, I see the first question is on using anaerobic filter kind of system, DWATS kind of system to treat fecal sludge. Yes, definitely you can, but that requires a process optimization and design. See, you can't directly use an ABR for treating fecal sludge because two parameters. For example, one is solid handling capacity, the loading rate, what you load versus the HRT or the SRT. Those will be impacting the entire treatment process. So that has to be optimized. So what we generally do is we design an biogas digester or an anaerobic stabilization reactor in combination with a dewatering unit like planted drying bed and unplanted drying bed. So you can look at options which will first deal with your solids, separate the liquid and solid in the fecal sludge. Then the liquid part can be still treated with the combination like ABR, AF and planted drying bed. But anaerobic systems have that buffer to handle more solids and organic load, even though there is a limitation, that is the nutrient removal capacity. They are little back when comparing to aerobic system in terms of nitrogen removal and phosphorus removals. So there might be a hybridization required if you want to achieve both nitrogen and phosphorus removal in the same treatment system. What is the second question, Division?
What kind of cost implications due to addition of FS to STP in terms of ONM of the STP?
You understand one system is there in your place. You are operating it at one particular capacity. For example, I'm having a 100 mld plant. I am operating it at 50% capacity. So there is different concepts, components involved. One is HR, then is the consumables, then the electricity and asset management. So there are four components that are involved in operating a system. So these components are not going to vary even if your FSTP is running at full capacity or half capacity. So ideally what it implies is when your capacity is underutilized, you are actually spending more amount of cost in HR, asset management, electricity consumption, everything per KLD comparison or per MLD comparison. But when you optimize your utilization to the full extent, this cost is eventually comes down to per MLD, lesser than what you are operating at half capacity. So in this way of understanding, when I add FS in a 50% utilized STP,